that is going to be exploring the notion of constant velocity for Physics 2211. Here's a table of contents for everything I'm going to cover today, and moving on to the introduction. So the purpose of these experiments will be to test Newton's second law and the momentum principle to empirically verify the fundamental principles of classical mechanics and understand the relationship to the motion of objects. We're going to do this by comparing the real-life scenario of a body moving in a horizontal line to its computational model, and in the process we're going to delve into not only Newton's second law, but also its first law. So a little bit of background theory before we begin the experiment. I'm going to define some concepts this investigation will be testing. So Newton once said that an object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an unbalanced external force, as demonstrated in the following picture in the first law. Whereas Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, given by the equation F equals ma as stated in this equation and shown in this picture. So now moving on to the equations that are going to be representing these concepts. This experiment will be based on the following equations, right? Force equals mass times acceleration, Newton's second law, that can be rearranged to give acceleration. And it will be plugged into the formula for final velocity as shown, which is the initial velocity plus acceleration multiplied by time, and this in the computational model as well as in the real model at very small intervals. This will be repeated many times to get the most accurate area under the curve. And the final position is going to be calculated by adding the average velocity, which is the average of the initial and final velocities, multiplied by time to the initial velocity. So to observe the effect of inertia on an object's motion, it is important to isolate variables that can affect the outcome. This means that minimizing the impact of external forces such as friction, air resistance, and other unwanted influences. In the computational model, the ideal conditions will be present, resulting in no net force. This is a little bit of a hypothesis. And hence, no net acceleration and a constant velocity will be present. And referring to the previous equations, final velocity will be equal to initial velocity. Whereas in the real-life model, we can hypothesize that inertia will be present, although effort will be put into simulating the most suitable conditions. For example, the experiment will be done indoors and on a smooth surface, but still the frictional force is expected to act in the opposite direction to movement, possibly slowing the velocity of the object down. It will also be interesting to observe whether the inertia will be statistically visible over a very, very short time interval that we're going to be doing this experiment in. So here's the model design, and the initial conditions for both my computational model and the real-life experiment. The initial position vector was based on the placement of the hand to the measurement rules. As you can see, the object was pushed from a little bit in front here, and the initial velocity was calculated in the following way using the video time interval and the distance the object traveled at the beginning. So here's an analysis. It's a video of the real-life experiment using tracker at 0.4 intervals to get the most accurate representation without complicating the graph, the values on the axes. The mass of the object used was measured to be 1 kilogram. As you can see on the output data, or on the more visual line graph, the start was slightly inaccurate despite the small time frame limit chosen. However, the rest of the motion demonstrates a strong linear correlation, curving very tiny slightly towards the end. Now moving on to the computational model, the mass in the code, explain the code a little bit, did not need to be changed because in the ideal model there's zero net force, hence in this final velocity equation the mass component will be eliminated as it's 0 divided by mass, but still I chose to use a 1, and so the equations, as you can see, for final velocity were inputted in the following way into the code. Give it here. The force net is 0, 0, 0. The time frame is 0.3, the same that was used in tracker. And the initial position and velocity are given here based on the model design that I previously explained. And so comparing the results, here are two graphs. This one is the computational model with the ideal conditions, and this shows the tracker model that has unwanted drag forces. And here is a graph comparing the two. So the y-intercepts are the same as the initial position coordinates were the same in both models. The computational model although gave an r-squared value of 1, a perfectly linear graph showing constant velocity, whereas the experimental data had a lower r-squared value due to the environmental factors such as inertia or perhaps slight wind. I don't know, but it is less linear. The gradient value, which is given in the green highlighted area, is representative of velocity. In the tracker experiment case, the value is 3.523, and it was smaller compared to that of the computational model value of 3.551. This is because of the opposing air resistance and friction forces that slowed the real-life velocity down, resulting in a lower gradient value. Real-life scenario was slower, but still, to my surprise, it was very, very close to the actual value. I was expecting it to be way less. I believe this is because of the small time frame chosen, which was 0.3 seconds. If the object was filmed in motion for a little longer, the gradient would definitely be even smaller, as the force of friction and air resistance would act for longer. So yeah, time interval and these values is a very important factor. Now moving on to further questions, the most apparent change would be, I respond to this what if question. The most apparent change, if we were to change the axes of the tracker, would be in the position coordinates of the tracked objects. If you originally had a positive x-coordinate for an object's position, it would become a negative x-coordinate and vice versa. This flip would affect the direction and the sense of motion of the objects. For instance, if an object was moving to the right, initially it would appear to be moving to the left after the axis flip. The same would happen to, not elements, but like values such as velocity and acceleration. In fact, all vector values being measured would switch directions. And on to the second question. It is really hard to tell how many forces are acting on a body in motion. If the velocity is constant, it can be said that the net force is zero, although if we're going to group the major forces together, it can be analyzed that the gravitational force opposes the normal reaction force, the push of the table, and the side push applied to the object cancels out the constant friction force to give net zero acceleration, but again, this is on very large scales. So yeah, thank you for listening, and see you in the next lab.